Good evening. Welcome to Lecture 9 of Topic 2 of Unit 4, Photoelectric Effect, the Theory. Okay, now this video will be covering the main ideas of Chapter 11.5 of Book 2. Please complete this reading before class. Here are your learning attention and success criteria for the chapter. Please pause the video and attempt to complete the KS table down on the right there. Okay, so we can see here that you'll be able to describe the photoelectric effect and solve problems related to different metals undergoing this effect. So we want to be able to describe it. There's some definitions we need to know, and we want to be able to do some calculations with this. So knowledge, what is it? What are these things? If we're going to define them, we need to know what they are, and what physical properties relate to the photoelectric effect if we're going to calculate some. In terms of skills, well, can you do some calculations? Now, this video is going to be a sort of two-part for the photoelectric effect. This first video is going to focus on observations and explanations about the photoelectric effect and with the relevant equations for it. The second is going to look at the experimental data, such as the graphs that you'd be expected to be able to interpret. That way you're hitting those things for the syllabus, just like we saw in the class experiment, but I wanted to make one on it because it's pretty much almost a guarantee that it will be on the exam. Now, one of the earliest examples of the photoelectric effect involved an electroscope, a UV light, and a piece of zinc. Now, we saw an electroscope back in Unit 3, Topic 2 in electrostatics, where you've got a gold foil attached to a small plate in a vacuum chamber. So there's a plate at the top, we can see here a little bit of gold at the bottom, and as this receives more charge, this slowly stands up on the side as the electrons spread out. So we charge up the plate either through a nearby charge or by just touching it with something. The foil stands up due to an electrostatic force. Now, if you put a piece of zinc on here and you negatively charge it, you could use electron transference by rubbing it, like with a Ferrin perspex rod, or you can charge it up using a current of some sort, and you put it on an electroscope. The foil stands up. This is negatively charged. Some of the electrons spread down. It's fairly standard. Okay, so we know about that. Remember, that's the electrostatic force pushing out. When you shine some visible light on it, nothing happens. It just keeps doing what it's already doing. So if we were to set this up in the classroom, we've got visible light obviously coming from the lights, nothing would happen. But instead, when you use a UV light, sometimes called a black light, the leaf collapses. Now, when the leaf stood up, it stood up because there were excess electrons. So for the leaf to collapse, the excess must be gone. And this was an observation that the UV light was removing the electrons. Okay, so this is the photoelectric effect. Alright, so let's talk about the experiments. The initial experiment, while Einstein gets a lot of credit for the photoelectric effect, most of this was done by a scientist of the name of Leonard. He set up a vacuum chamber, so meaning no air, with two metal plates. Kind of look like this. So we have an it's called a photocell, but it's just an evacuated piece of glass, and you have a piece of metal here, which we're going to call the cathode, a piece of metal here called the anode, and they're hooked up to a circuit by a piece of metal going through the glass. Now, just as a really important point, this is a cathode ray tube, but for a really important point, the cathode here, okay, is the negative side, and we connect it to the negative terminal of the battery. The anode is the positive side. The way I always interpret is by looking at the diagrams, but in case you don't get a diagram of the circuit, you are going to have to need to know that. And this is different from how the words are used in chemistry if you take chemistry. It won't matter significantly, just try to be aware of it. So this cathode ray tube, we put it into a circuit like this, and over here on our microammeter, nothing happens. Okay, the battery here, you can't run current through the air too well, or through a vacuum too well. You can do it, but it takes a lot of voltage to do it, and little batteries aren't going to do it. So this was the setup, and nothing happened. Now, what Leonard did was he shone light onto it, like this. He shone light onto the cathode, and stuff started to happen. So he tested different frequencies. And nothing happened until he reached a minimum level, okay, which he called the threshold frequency. Now, you have to be able to define this term. As the frequency increased past that point, the photocurrent, the current caused by the light, also increased linearly. Okay, so the light was ejecting photons. Sorry, the light was ejecting electrons. The photons were ejecting electrons. And these electrons were traveling and creating a current, creating a circuit. If you're above the threshold frequency, you increase the intensity or the brightness of the light. The light also increased the current. Okay. But if below threshold frequency, like if you were 1 hertz below the threshold frequency and you made it as bright as the sun, it didn't do anything. Okay, so it had to be at that minimum level or above. So this was his first experiment, looking at the frequency of the light and what that did, and we saw similar in the simulation, which we'll talk about next, or next video. In the second experiment, Leonard looked at voltage. Okay. When he increased the voltage in the circuit, and so it made the positive side, the anode, more positive, and it made the negative side more negative, nothing happened. But when having the voltage point the opposite direction, so flipping the battery around the other way, and making the anode, here this bit, have a bit of a negative charge on it, the current starts to slow down. Okay, so making the net voltage negative reduce the current. If you put enough voltage on it, it stopped the current from flowing, and he called this stopping potential. Remember, the word potential is basically synonymous with voltage. Sometimes, in fact, you have it called stopping voltage. Sometimes I will use that word. And the problem was that none of these observations that Leonard made could be explained by light as a wave. Now, after Planck did his work on the idea of quanta of light, Einstein in 1905 wrote a paper that resolved these wave issues with photoelectric effect by using this idea of the quanta and led it to the concept of a photon, a quanta of light. Okay? The smallest packet of light. And he re-examined the photoelectric effect experiments, he redid them, and identified the following energies in the system in using this idea of the quanta of light, or quanta of energy. So the first off was the photon energy. It involved light. Planck said, hey, maybe this actually has some sort of packet sizing, and so he used this formula E equals HF to work out the amount of energy in the light itself. He defined this idea of the work function or binding energy of the metal with this equation. Okay, work equals H times F naught. Now let's just look at that for a second. Work is energy, E, W in this case, they're basically synonymous, H for H, and here we have just a special type of F. So this equation here is just this one rewritten to talk about a specific thing. The reason I put it down as W is because we're going to see it in an equation in a second. But this is an important thing. I did prove it to you in class how to get it, but it may just be easy to memorize. Now, to work out the kinetic energy of the electron when it was left, he used electrostatics, and that was given by this formula that the kinetic energy of the particle is the charge of the particle multiplied by the voltage needed to stop it, so that's stopping voltage from the second experiment. And this equation does not appear under the quantum mechanics section. It appears under electrical circuits. It's a rewrite of this one. Remember, work is just energy. Okay, so when he reversed the voltage on the battery, he did some work against the charge. He knew the voltage from required, and he knew the charge of it because there was an electron, and so he knew the amount of work that had to be done. Okay, so let's look at what we've got here. We've got some energy, okay, being given. We know the energy of the electron because we're working against it using voltage, and we know this minimum energy to get it off the electron, off the metal in the first place. In this case, well, we've just got two different types of energy, and so they've taken the sum of it. In this case, that the kinetic energy of a particle equals HF, okay, where F is the incoming light, take away the work of the energy, or the work function. This has to be in joules, and H times F will result in joules. Sometimes you'll see it written like this, where it's HF minus HF naught, because that's what work function is. Or if we factorize it, H outside of F take F naught, and this will give us the kinetic energy of the particle. So let's have a look at some examples. This is a fairly standard type question of just doing calculations, not using the experimental data. A threshold frequency for a metal illuminated by violet light is 6.93 times 10 to the 14 Hertz. Determine the work function and then identify the likely metal. Now in this case, the fact that we're told it's violet light is just a misdirection. We don't need to do anything with that, because all we need to do is work out the work function, and then we work out the metal from looking up a table. So we have here our threshold frequency in Hertz. We're going to need the work function, and then we're going to need to convert it into electron volts so that we can match against the table there. So let's get that out of the way. So we're told F naught 6.93 times 10 to the 14 Hertz, and we know the work function equals HF naught. In this case, pretty straightforward. Let's substitute in Planck's constant. Which will give us an answer of about 4.59 times 10 to the negative 19 joules. We need to convert that to electron volts though. Remember, to turn joules to electron volts, we divide by the constant, the charge on the electron, which is that 1.6 times 10 to the negative 19. Well, those are just going to cancel each other, so we've got 4.59 divided by 1.6, which equals 2.87 electron volts. And if we go back to our table, ignore the big light there, we can see that that matches up with calcium. Therefore, Ca. Now, the second part, oh yeah, there's the second part. I'm going to do a little bit more on this question, just because it hasn't been asked for here, but I want to show you how we would go to the next step. Now we're told it's violet light, violet. So I'm going to assume the wavelength is, let's go about 400 nanometers. Okay, could be a bit lower, but it's a good assumption. We can work out the frequency for that, because remember, we know that the velocity of a wave equals the frequency times the wavelength, or that the frequency will equal the velocity of the wave divided by the wavelength. In this case, the velocity is our constant c, the speed of light, because we're dealing with light. So that equals 3 times 10 to the 8 divided by 400 times 10 to the negative 9. Remember, nanometers is 10 to the negative 9. So our frequency, 3 times 10 to the 8 divided by 400 times 10 to the negative 7 is 7.5 times 10 to the 14 Hertz. So that's the light that's being shone onto it. And the good thing is, if we look at the threshold frequency here, this number is bigger than this number, which means that this is the amount that's being taken away just to get the electron off, to ionize the electron, and this is the amount that's being given. So there'll be a bit of energy left over to give it some kinetic energy. If we were to substitute into that formula, kinetic energy equals HF take work. We've already got the work figured out, so that's good. 6.626 times 10 to the negative 34 times 7.5 times 10 to the 14, take away 4.59 times 10 to the negative 19 equals, the way I would do this is I would process this bit first and then take away this bit at the end. I should get a number that is going to, because this times this, negative 34, 14, that's going to cancel off and be about negative 20. That times that's going to be a little bit bigger, so it'll be 10 to the negative 19 in magnitude. So I'd still expect a number around the 10 to the negative 19 point. It is always good to check your math a little bit mentally and have an idea of what's a reasonable answer. Okay, so this bit over here is 4.9695 times 10 to the negative 19. Take away 4.59 times 10 to the negative 19. So we can see here 4 take 4 is going to cancel, 9 take away 5 is going to be 0.4, 6 take 9 is going to drop that down to 0.37. So it's about 0.37 times 10 to the negative 19 joules, or 3.7 times 10 to the negative 20 joules. You can do that last step on your calculator if you wish to, but sometimes it's just good practice for yourself to do it in your head while you're doing these things so you know what's reasonable. Okay, because remember, I don't trust calculators. Often the next step, and we'll see this in the next example, is to take this kinetic energy and work out a velocity, because remember we've seen in last year for all of you, because you did it in year 10 and you do it in year 11 and unit 1, or the current year 12s did it in unit 1, that kinetic energy equals half mv squared. Well, this is a kinetic energy. Okay, we've worked out that energy. And the mass of an electron, because remember this will be the mass of the electron, is a constant that is given to you in your, sorry, move that up a bit, in your formula booklet. So that could be that it's something that's asked, and the good thing is the next example asks us to demonstrate that. So let's have a look at that question for our next example. Let's straighten that up a bit, sorry. Okay. So a second example here, a barium metal cathode is illuminated with 420 nanometer light. Okay, determine the maximum kinetic energy and the velocity of the photoelectron if the work function is 2.52 electron volts. The mass of an electron is 9.1, blah, blah, blah. But again, remember, that's a constant given to you in your, what's the word I'm looking for? In your formula booklet. Now, while Walding does mention that you can do this in either unit, in electron volts or in joules, it is well worthwhile just doing it in joules, just so that you avoid annoyance. Feel free, you've got to be able to convert joules to electron volts if the answer is asked to be in electron volts, or if you have a table like we saw there and your numbers are in electron volts, you might need to match something up. But don't worry about doing things in electron volts, because it's just an extra, as well as in joules, it's an extra level of complexity, and the time it will take you to get the habit down pat could be spent much better doing other things. So we're going to do it in joules. Part B actually gives us the work function. If it didn't give us the work function, I would have to scroll back up to that table, although in this case barium is not even on that table, but if it was not provided to us, we'd have to look it up. We know that the work function in this case is 2.52 electron volts. So that's going to equal 2.52 times 1.6 times 10 to the negative 19 joules per electron volts, which will give us some number, 2.52 times 1.6 10 to the negative 19 gives us a work function of 4.032 times 10 to the negative 19 joules. And we are told it is 420 nanometer violet light. Lambda equals 420 times 10 to the negative 9 meters. As a hint, I would recommend you just convert to meters immediately. Don't even bother writing down the word nano. Let's convert that to a frequency, because we can't do much with wavelength. C equals F lambda. F equals C over lambda equals 3 times 10 to the 8 over 420 times 10 to the negative 9. 310 to the 8 divided by 420 negative 9 is 7.1, let's round that off to 14 times 10 to the 14, and that's in hertz. While units aren't important while you're working, just keep it in mind that if getting used to writing that can be beneficial. All right, now we're after the maximum kinetic energy, so EK equals HF minus work. So 6.626 times 10 to the negative 34 times our frequency, 7.14 times 10 to the 14. Take away our work function, 4.032 times 10 to the negative 19 equals a final answer of about 0.7 times 10 to the negative 19, and if this was your answer, you must make sure that you convert it properly, 7.0 times 10 to the negative 20 joules. If you have something like this, make sure that you convert it so that your first digit is not a 0. Really important for communication. So there's our average kinetic, well, there's our maximum kinetic energy. And you could be asked to convert that into electron volts. That's not a problem. We would just divide by 1.6 times 10 to the negative 19, and you'd get some electron volts, and you can see it's going to be about 0.4-ish electron, 0.4 electron volts. Now the second part of the question was, what is the velocity? Yes, what is the velocity of the electron? So B. So this is kinetic energy, and so now we're going to have to use this idea that kinetic energy equals half mv squared. We've got our kinetic energy, and our mass must equal 9.1 times 10 to the negative 31 kilograms. Remember, I would imagine on an exam, you're probably not going to get prompted. Sorry, that's rolling a bit. You're probably not going to get prompted for this number. It's likely that you'd be expected to realize, oh yeah, it's kinetic energy. I know the kinetic energy formula. It's in my formula booklet. Let's go and have a look at that and go, yep, here we go. So now we're just working out V, so let's substitute these in. 7.0 times 10 to the negative 20 equals a half times 9.1 times 10 to the negative 31 times V squared. And if we rearrange all that, multiply the 2 over, divide by the mass, take the square root, we're going to get an answer that V would equal 3.9 times 10 to the power of 5 meters per second. Okay. Really important though, really important when you're doing these things. Double check that this is not 10 to the power of 8, especially not 10 to the power of 9. If it's 10 to the power of 8, you might be okay if you have really, really high energy light hitting a piece of metal, because as long as it's under 3 times 10 to the 8, you're okay. But remember, some of these things, you're going to be getting into that sort of special relativity, very fast particle sort of stage. So just double check that you've done the correct answer. For example, if you forgot to do the square root, the answer for that is 1.54 times 10 to the 11, which is more than 10 to the power of 8. So that would be faster than the speed of light. And a good check step should really have you going, small particle, but it's way too fast. So I need to just double check that that something hasn't happened there. But yeah. All right, that is our last example. Make sure that we can see that. A bit wonky, there we go. Alright, so in this video we have looked at the following. We've described how the photoelectric effect is caused by photons. We've defined those important terms of the photoelectric effect. Okay? And we've done calculations involving the photoelectric effect, and I've forgotten to change the success criteria there at the bottom. Just go back to the start of the video. Maybe I'll fix it up next year. For your entrance to class, please complete questions 1 to 6 in Chapter 11.5 Check Your Learning PDF and copy your answers for them into the 4.2.9 space on eLearn. Thanks very much for listening, guys. Have a great night. Bye.